Greetings everyone. Today we're going to be talking about the first law of thermodynamics. The first law deals with energy conservation, that energy can't be created or destroyed. So we talked about how you can use energy to do work. Say if you wanted to hike up this mountain, you would have to expend some amount of your internal energy in order to gain this potential energy, but the total energy of the system would still be zero. And we also talked about how heat is a form of energy. The first law puts these two ideas together. So let's talk about work first. So if we take a cylinder and we put some gas molecules inside of it, now we're going to imagine that the cylinder is going to expand upward. So maybe you heat up this gas and then it moves the piston upward, and so the gas expands. So what would you expect the work done by the gas to be? Is it going to be positive or negative? The work done by the gas, we're going to do this integral of P dV. And since we're just going to assume P is constant just for simplicity, but P will always be positive, so that's not going to change what's going on here. So then V final minus V initial. And if V final is greater than V initial, which it is expanding, then the work is going to be greater than zero. The flip side is that if this gas is shrinking in size, then the work done by the gas will be negative. So the first law of thermodynamics says that energy can be transformed. You can transform it to heat, you can do work with it, you can store an internal energy of the system, but you can't destroy it or create more energy. So that's his first law. So this Q is the heat added to the system, and then the work here is going to be the work done on the system. So if you recall from that last slide, the work done on the system has this negative sign here. Then this internal energy is equal to this D is our degrees of freedom. So for a monatomic gas, you just write a 3 here. For diatomic, you'd write a 5. N kb delta T is going to be equal to the heat added to the system and the work done by the system. So if the system is doing work and you're not adding any heat, then the temperature is going to go down. So that's how all these things are related to each other. And the last thing that I'd like to include here is the entropy of an ideal gas is going to be related to the volume and related to the temperature, plus some constant. But this constant doesn't play a big effect because when we look at ds, then this constant falls away. For those of you who like conclusions and not lengthy derivations, here's a collection of all the formulas from this chapter. We have relationships between dt and the amount of work. Heat or internal energy is related to the system or the change in volume. And this can be really handy for engineers and the like, but I actually want to dissuade you from using such a chart because I want you to focus on just these three relationships, and all the problems that will work and that you'll see in this class will only deal with these three equations. You will not need to go back and use this. Basically just the definition for work by a gas and for entropy and this first law relationship. You will need to know that adiabatic, that the amount of heat transferred is zero, or that this isothermal energy, there's going to be no change in thermal energy because the temperature stays constant, or the isochoric is going to be zero, but we can get each of these from our relationships, just these three simple equations. The less important thing is how entropy changes during a phase transition. This can be melting, vaporization, condensation, solidification. What I'd like to point out here, though, is that this sign is really the most important part. How does entropy change during that phase change? And so if you're going from condensation, from gas to liquid, or solidification, liquid to solid, then your entropy is actually going to decrease. Whereas if you're melting or vaporizing, then the entropy increases, so this number is positive. We have 1 mole of some ideal monatomic gas. It is sitting at 73 Kelvin, so that's our initial temperature. And then it's going to absorb some amount of heat energy, so that's Q. This is our 100 joules. What is the final temperature? So what I want to find is T final. And we're going to assume that the volume doesn't change. So now we need to ask ourselves, how does this come into play? If we look at the first law of thermodynamics, then our change in internal energy is going to be related to Q plus the amount of work that's done. So I have Q. I would like to find T, so how do I relate T to these guys? Well, I know that my change in energy, in thermal energy, is related to the temperature. And that's by 3/2. This 3 is because 3 degrees of freedom for monatomic. And then N, Boltzmann's constant. And then now times dt. You can also relate this to the V squared. That's the kinetic. This is the kinetic energy in the gas. So I have a way of relating temperature change with this E thermal. And so now I need to know, how can I get from Q to here? So I need to relate work to something. So the work is going to be minus the integral of P dV. This is the work done on the gas. And so then dV is going to be 0. So for us, this is going to be nothing. So then this internal energy is just going to be equal to Q, which tells us that we have 3/2 in kV delta T. It's just going to be equal to 100. So then what I really want to solve for is delta T, and so then that's just my 100 joules all over 3/2 in kb. So then T final is going to be T initial plus delta T. And when I plug that in, I'm going to get about 80 Kelvin. Let's look at the work done through a thermodynamic cycle. And we're going to be looking at it in a P versus V graph. So what is the work done if we go from 1 to 2? So for all of these, we're going to be using the work done by the gas. So this is integral of P dV without the minus sign here. So this is by the gas. And so there's no minus sign. So then P dV from 1 to 2 is just going to be the integral of P dV. And then now we just look at P. P doesn't change, so we can bring that out. So that's our 3P0. And then now V final minus V initial. So V final is 3V0 minus V0. So then this is equal to 6P0 V0. And the units of this are joules. So now what if we go from 5 to 6? So we're basically doing the same thing here. The integral of P dV is then going to be equal to P, but P here is just P, not 3P. And then final is 3V0 minus V0. So this is equal to 2P0 V0. So now let's look at going from 2 to 6. Choose a different color. From 2 to 6. So here if we look at PdV, our V isn't changing, so we're actually going to end up with 0. Here we can go from 1 to 3, 3 to 6, but we can note that it's actually just one continuous curve from 1 to 3 to 6. And we can then use, we can either solve for P as a function of V, or we can just note that this is actually going to be the area under this curve. So then we can take the area of this triangle and then add on to the area of these two little boxes down here. So what we're going to have is the area of the triangle, which is going to be 1/2, and then the base is 2V0, and the height is 2P0, And then now we're going to add on these two boxes, and that's 2 V0 P0. So this 2 cancels that 2, and now we're left with 2 plus 2, so we're going to get 4 P0 V0. Alright, and now for the last one, we're going to follow 1 to 2, so that's this curve, 2 to 6, 6 to 5, 5 to 1. So then what is our work done for this cycle? So we basically need to sum up the work for each of these components. And so from 1 to 2, well, we already did that, and that's our 6 P0 V0. From 2 to 6, that guy was 0. And then from 6 to 5, well, we did from 5 to 6. But if you make a process go backwards, you end up putting a negative sign in front of it. So this is actually minus 2 P0 V0. And then we're going to add on another 0. So then this is going to be equal to 4 P0 V0. Another way to think about this guy, this for the E component, is when you do a cycle, you're really getting the area inside that cycle. So the amount of work done is just going to be this cube. So this is 2 by 2, so I should just get 4. We all know that hot air rises because it's less dense than cold air. So then, why is air in the mountains colder than air in the beach? So if we look at the mountain, we know that air up here is colder than down here at the beach. So let's just say we're at the beach. Our temperature is maybe 25 degrees C. It's not the biggest number, but and that's about 298 Kelvin. And our pressure is just 1 atmosphere, or 101,325 Pascal. Let's just say we're not climbing all the way up the mountain, but let's just move the air up some small little step. We're just going to move it up 100 meters. So not all the way up to the top of the mountain. Just going to take some air, some wind, and blow some patch of air like this. Take this patch, and then now we're going to blow this patch just from here to here. So we know that P equals P0 plus rho GH. And so the pressure up here is actually going to be less than the pressure down here because there's less air sitting on top of this. So then we actually get that the pressure here is going to be equal to 101,325 minus the density of air times 9.8 times our 100 meters. Sorry, just 100. So then the pressure up higher, pressure 2, is not going to be a whole lot less. It'll be a little bit less. So 100,123 Pascal. So we're not taking into effect that this density changes with height. Then we can say that this gas is going to undergo adiabatic expansion. It's not leaching heat, adding heat from some other external source. So then that's PV to the gamma is some constant. And then so we're going to have P1 V1 to the gamma is going to be equal to P2 V2 to the gamma. So what we really want to find is this V2. So V2 to the gamma is going to be equal to V1 to the gamma. And then now we're going to have P1, P2. We divide P2 over to this side. And then now we need to get rid of this gamma. So we have gamma's up here. And what we're going to do is to go to the 1 over gamma power. And so that'll get rid of this one and this one. And so then we have V1, and then we're going to get some ratio of these two pressures. So P1 is 101.325, and then P2 is 100.123, and then now we do this to the 1 over gamma, and 1 over gamma is going to be 5 over 7. And so then we're going to get that V2 is equal to V1 times 1008. So not a whole lot different. It's not going to expand a whole lot, just 8 parts per thousand basically. And so we want to see how the temperature is going to be changed. So we're going to use our ideal gas law. And so then PV over T is going to be a constant. And so then P1 V1 over T1 is P2 V2 all over T2. So then our temperature 2 is going to be the same as temperature 1, and then now times P2 V2 all over P1 V1. So now we have this ratio of these two volumes. So V2 is a little bit bigger than V1, so we're going to put in that. Basically, we can separate these two. P2 over P1, and then V2 over V1. So V2 over V1 is going to be our 1.0085, and then P2 over P1 is going to be this divided by this. And when we plug these in, we're going to get that T2 is going to be 297 Kelvin, pretty close. So we have lost about a degree by going up just 100 meters. And this is because of this adiabatic expansion. So let's look at how entropy changes as we go through a cycle. So unlike work, where it really depends on which path we take to get from some initial state to a final state, entropy does not depend on which path that we go. We could take this A path, or we could take this B path here, and our change in entropy would be the same. So here again we're going to need our ideal gas law, N KT, and let's just go ahead and solve this for T. So T is going to be equal to PV over NK. So what I really want to know is the change in entropy between 1 and 3. Then I could take 1 as my initial state and 3 as my final state. So then at state 1, I have P1, I have V1, and I'd like to know T1. So then T1 is going to be equal to P1 V1 all over number of molecules K. And now at 3, we're going to have P3. P3 is equal to 3 P1. And then we're going to have our volume. Our volume is 3 V1. And so then T3 is going to be equal to P3 V3 all over NK. Now to find the change in entropy, what we're going to do is say S3 minus S1. That's going to be our change in entropy. So then we're going to get N ln V3 plus D over 2 N ln of T3 minus N ln of V1 minus N D over 2 natural log of T1. And we're not going to care about that constant because it's just going to drop out. So I'm going to take these two terms and combine them. Then now take these two terms and combine them. So my delta S is going to be equal to N times the natural log. When I subtract two terms, I get to divide inside the natural log. And then now I have D over 2 N natural log of T3 all over T1. So now I can start plugging in a little bit of what I know. Natural log of V3 So v3 we said was 3 times as big, so 3v over v, and then we're going to add on d over 2 in natural log of our t3. So t3, this is actually equal to 3 times 3, that's going to give me 9 pv over nk. And so I'm taking this number and dividing it by this, so I'm going to get 9, basically t over t. So now my change in entropy is going to be n times the natural log of 3 plus d. And d here, I'm going to assume this is a monatomic gas. And so now I'm going to say d is 3, so I can move forward. So I'm going to have 3 halves in natural log of 9. And natural log of 9, I'll just write it up here. Natural log of 9 is equal to the natural log of 3 squared. What you can do is you can bring this 2 out front. So then you get 2 natural log of 3. And so when I do that here, I'm going to get n times the natural log of 3 plus 3 times n times natural log of 3. So I get 4 n natural log of 3.